Hi everyone, hope you're doing well. So first thing today that I want you to do is the warm-up. So in your notes on pages 12 through 14, I want you to go through examples 1 through 6 and just decide if the pairs of figures are congruent. And then if they are, I want you to name the rigid motion or more than one rigid motion that'll map one figure onto the other. So our goal today is going to be proving that these figures are congruent. So the first step that you guys really need to do is be able to identify are they congruent and by which rigid motions make them congruent. So go ahead and do that. So go ahead and pause the video, give yourself like 5 to 10 minutes to do that. Make sure you record your answers on your warm-up sheet because I'll be checking those. And then we will complete the notes together. So go ahead and pause the video right now to do that. All right, so hopefully you've completed 1 through 6. So let's actually go through and look at the proofs for those. So this will be a good way to kind of check to see if you were right on track with the warm-up. In terms of last night's homework, the pages 9 through 11, we're going to talk about those next class. So just kind of leave those and we'll worry about them next class together. So for example 1 in your notes, so I'm on page 12. Our first goal, well, on your warm-up, was to determine which rigid motion would take one figure onto the other. So for this one, I'm always going to call this first triangle that's listed on the left triangle 1, and then I'm going to focus on how did I map that triangle onto this triangle here. So triangle 1 getting mapped onto triangle 2. Hopefully you found that if you draw the arrows on, you see that they go in the same direction, so a translation is what occurred. So it's going to be a translation by moving right 3 down 5. So it's a translation of 3 comma negative 5. So that's what we talked about last class. So kind of coming up with that. So then the next thing is, yes, they are congruent because we found that a translation maps one triangle onto the other and a translation is a rigid motion. But now we actually want to write up a formal proof. So yesterday's notes, we were just trying to determine the rigid motion and we were just trying to explain it. Today we actually want to be more specific and write a formal proof. So I'm going to start with the T, statements, reasons. And these are going to be very similar to those parallel line proofs, where the first thing you have to do is you have to take each of the points and perform the translation. Instead of saying a translation along a vector, since this is on a graph, we can be more specific and say 3 comma negative 5. So I'm going to start off, I'm going to have 3 points that I'm translating, and they're all going to be translating using 3 negative 5. I'm going to go ahead and write that 3 times. So that's going to be my rule. My inputs here are going to be the points from this blue triangle, so it's going to be A, B, and C. So those are going to be my inputs. And then your outputs are going to be, well, what did these points map to? So A, when I moved right 3 down 5, became G. B, when I moved right 3 down 5, became H. And C, I moved right 3 down 5, became I. So that means ABC mapped to GHI. And the reason for this is you did a translation along, either you can say the same vector or along vector 3 comma negative 5. And I'm using that vector notation there. So now, since I have shown that these 3 points mapped, now I have to actually show that that means that the whole triangle maps. So all of these other points on the segments mapped. So second step, just keep the order right here. So triangle ABC mapped onto triangle GHI. And if you notice right here, it matches the order of the letters over on this side, which it always should. So A should always get mapped to G, B should get mapped to H, and C should get mapped to I, because the order over here is important for this. It's called a congruence statement, so that order is important. So the reason for the mapping here is because translations map triangles onto triangles. So as long as you translate a triangle, you're going to get out a new triangle. So then, therefore, we can say that these two triangles are congruent because we've just found a rigid motion that maps one onto the other. So, same reason that we've been using the last few days. So, two figures are congruent if and only if a rigid motion maps one onto the other. So this proof should seem very familiar to the proof that we've done the other day with the parallel lines. So very similar process where you have to show each point, then you show the mapping, then you show that they're congruent. So let's try another one. So for the warm-up, you were supposed to identify, are they congruent? So you should have said yes, and then the reason for why they're congruent is because if you compare, so again, I'm going to call this one triangle 1, this one triangle 2, and if I'm looking at how did I go from one to the other, I did a rotation. So the rotation that occurred, you have your center of rotation, was a 90-degree rotation. So this was a rotation of 90 degrees to get from one point to the other. Now, I know a rotation occurred because the orientation stayed the same, and then I just compare, so the first point here, A, to the first point, T, and it was a 90-degree angle. So now we can go ahead and write up this formally. So first thing here, we have 3 points that we need to rotate. Rotation of 90, so I'm going to write it 3 times. Now remember, you don't have to write rotation 0, 0 for the origin, so don't worry about that. So I have my input points are going to be triangle ABC. So remember, they should match the order over here. So ABC is what I'm starting with. When I rotate A, it's going to T, so the output is T. If the input's B, the output when I turn that 90 degrees is going to be over here at K. So again, look at that 90-degree angle. And you can also look over here. B's in the middle, so K is the one that it has to correspond to. And then C and H. So again, you should see a 90-degree angle. So the reason for this is I just did a rotation of 90 degrees around the origin. So you don't have to write 0, 0 because it's just assumed if it's not listed there. So then the second step is to say, well, that actually makes that triangle map onto the other triangle. So that means triangle ABC must have mapped onto triangle TKH. Reason for that is because rotations map triangles onto triangles. So if you start with a triangle, it'll map onto a triangle. So then the last thing here is to say that these two triangles are congruent because we found a rigid motion that maps one onto the other. So remember, rigid motions are preserving all of the segment lengths and all of the angles, meaning overall the figures have to be congruent. They're the same shape and same size. So our reason for this, two figures are congruent if and only if a rigid motion maps one onto the other. So again, very similar to that last proof that we just did. Same format, same number of steps. The only time the number of steps is going to change is if you're doing more than one rigid motion. Then you would have to state those rigid motions, and then the differences in your final step. You would say two figures are congruent if and only if one or more rigid motions maps one figure onto the other. So let's look at example 3. So talking about more than one rigid motion, example 3. So this dotted figure here is really kind of showing you the in-between step. So what's happening is we're looking at triangle BCD. So this triangle here is number 1. And your notes should have this fixed, EGF. It should be worded like that. So if we compare from here down to this triangle, this right here is an in-between step. So we took this triangle 1, we flipped it over line L, and then we translated it along vector V. Notice this one's not on a graph, so we're not going to be as specific. We're going to say it reflected over this line L, and it translated along this vector. So when we go to write this up, we're going to have more than just 3 steps because we have more than one rigid motion that occurred. So you have your statements, reasons. So the first thing is going to be, how did I get from triangle 1 down to this dotted line triangle? Because you have to flip it first before you can translate it. So step 1 is going to be the reflection. So I'm going to reflect over line L. So notice the subscript here says line L because that's what I'm reflecting over. And I gotta identify my inputs and then my outputs from that. So basically, if I take point B and I reflect it over this line, I'm just gonna call it B prime. It'll become B prime. So B will go to B prime. C is gonna go to C prime. And then D will come to D prime. So the reason for this is I did a reflection over line L. So those are all my pre-image points getting mapped to these image points. Now typically step number 2 is to show that this triangle got mapped onto B prime, C prime, D prime. But remember, since I have to do another transformation, it's going to be easier instead of writing that step, like doing 3 steps for the reflection, 3 more for the translation. It'll be easier if we just group them together. So what I'm going to do now is I'm going to go ahead and I'm going to do the translation. But when I do the translation, I'm going to use these points right here. So those are the points I want to translate. So I'm going to do a translation along B for my 3 points. So I have B prime, C prime, D prime is what I'm translating. So now we have to look at what we're going to get out. So when I translate B prime, that's going to move to E. So this will equal E. C prime is going to move to G. And D prime will move to F. And remember, in the end, you should be getting out these coordinates because that's what we're trying to show. So the reason for this is a translation along vector V. So now the next step is to actually show the mapping. So what I'm going to do is I'm going to show that this triangle got mapped to this triangle. So the primes here. And then I'm going to show that the primes became this triangle here. So when I go to write it, the first triangle was triangle BCD. That got mapped to triangle B prime, C prime, D prime, which then got mapped to triangle EGF. So I just combined that step. So then the reason for this, instead of saying reflections map triangles onto triangles and then translations map triangles onto triangles, I'm just going to say reflections and translations map triangles onto triangles. So then therefore, since I've shown that this triangle that I started with got mapped to triangle EGF, that means that those two triangles are congruent because I've used a rigid motion to get from one to the other. So step 4 will be triangle BCD is congruent to triangle EGF because two figures are congruent if and only if one or more. I'm using one or more because it's not just one rigid motion. I've used two rigid motions. So two figures are congruent if and only if one or more rigid motions maps one onto the other. So maps one figure onto the other. So then the next thing I want you guys to do is example number 4, and then you're going to work through 4, 5, and 6. Whatever you don't finish will be homework, and then we will go over them on Monday, but I will be checking those before. So I want to give you a couple hints for those next ones, just so that you kind of know what to do. But the setup of the proofs are going to be very much the same as like what we just did. So same setup, it's just first you have to identify how did I go from one triangle to the other. So let's flip the page and look at example 4. So example 4, remember we're going to call this one triangle 1. So we're starting at triangle 1. This is going to be the in-between step, and in the end you're trying to get to triangle 2. So here's your triangle 2. So for this one, it's going to be the same number of steps as the last proof. So you're going to have 4 steps in this proof because you're going to have your 2 rigid motions plus your ending statement and your mapping statement. So if you look at how I go from triangle 1 onto this dotted triangle, what's happening is a reflection because C will become C prime. B is going to come up here to become B prime, and then A will come up here for A prime. So your 2 steps, or your 2 rigid motions, are you're going to do a reflection over the x-axis because you're flipping this up, and then you're translating. So I'm going to let you guys figure out the translating part, but you will be doing a translation. So just figure out how did you go from here onto point D. So 4 steps total. And then the next one, you're going to have 4 steps as well, because this one, they don't tell you, they don't show you the in-between step, but if you look at going from triangle ABC onto this triangle here, so starting here and getting here, you're going to have to do a reflection. It's going to have to flip over the y-axis, but then you're also, because if you look at the way that the triangle is, it's flipped. You could tell by the letters, if I draw on my arrows, I'll see that they go in opposite directions. So if you just draw on these arrows, you know a reflection occurred. But you can't just do a straight reflection. It's going to then have to translate. Or you would translate first and then reflect, but it's definitely easier to do the reflection first, and then wherever you get, whatever triangle you get out, then just translate it. So this is going to have 4 steps as well because there's 2 rigid motions, so it's very similar to example 3 and 4. And your 2 rigid motions, you're going to do a reflection over the y-axis first to get your new triangle, and then from there you're going to do a translation. So you'll just have to figure out how did I move that new triangle to get onto triangle 2. And then the last one that I want you guys to do is example 6. So example 6 is probably the most complicated one just because there's more steps to it. So you're going to have a total of 5 steps for your proof for this one because you have to do 3 rigid motions. So you're going to have to do 3 rigid motions, and then you're also going to have to do your mapping step and then your final statement. So for this one, there's going to be a translation involved, there's going to be a rotation, and a reflection involved. So you're trying to prove that triangle ABC is congruent to DEF, and if you look, we're going to start at triangle 1, which is right here, and you're trying to map onto triangle 2. So first thing you're going to want to do is a translation. And then what you're going to have to do, so first you're going to translate it, and it should end up somewhere down in here. So it's going to end up looking like this. So B prime, C prime, A prime. So translate it. So do a translation first. Then once you've done a translation, you can rotate it around this point here. So then it should end up looking like a rotation. So it's going to have to turn 90 degrees. So you're going to do a rotation around point C prime of 90 degrees. And then from there, you can reflect over this line right here. So you're going to end up reflecting over this, and that'll get you onto triangle 2. So this one's definitely the most complicated, but hopefully with these steps, you'll be able to figure it out. So reflection over line DF. Okay, so follow those steps. When you do the translation, just tell me what you're counting by. Everything else, notice I didn't put like an equation or an axis because this is really, the grid's just there to be able to count for the translation, but we don't know where the origin is. So we're not going to use any lines. We're just going to say like for the reflection over segment DF. So go ahead and try those 3 examples, write up the proof using these steps. And have a great weekend. I'll see you guys on Monday.